And then as we go here, the situation becomes worse. So here there's no QK cohomology. There is N cohomology, where this is the unipotent radical of some parabolic. And this translates into that there is a realization in coherent cohomology of what is, we could call Griffith-Schmidt manifolds, or following Griffith's Mumford-Tate manifolds. The problem is that in this case, these are probably no longer algebraic, and here there is no N cohomology and no known relation to algebraic geometry. Okay. Yes?
I want to ask, is this true for all degenerate limits of discrete series that there's N cohomology?
Yes, I think so.
Next to last point, you actually always have coherent cohomology if you have some degenerate limit.
I think so, yeah. So there is a paper by Sorgel which computes in some sense the N cohomology of a general degenerate limit of discrete series.
And it's for any group, not only unitary group.
Yeah. So it's in terms of quite complicated combinatorics of the Weil groups, but
No, I understand this, but if you pick
yeah.
limit of discrete series which exists, although there's a degenerate, then there is a cohomology.
Yeah, I think to determine exactly the degrees in which it occurs and the dimension might be hard, yeah. Whereas here it's always one-dimensional. And if we assume that the real points are connected, then occurs in 1 degree only. Okay. Okay. And then about what I said about, so this maybe explains why when we go this way, things become more difficult. And now let me quickly say something about the more interesting. So, I mean, we might be interested in, well, I think two of the most interesting things that you might want to get as RL of pi are the Tate module of A, where A is an abelian variety, or to get an Artin representation and so I just want to point out that in these cases, very quickly, we wind up over here. So if I look at the case of abelian varieties, if I look at the dimension of A and pi infinity, then when this is 1, this is elliptic curve. So this is discrete series. When this is 2, this is a holomorphic limit of discrete series, and the group is GSP4. And when the dimension is 3 or more, then this is already a degenerate limit of discrete series. The same thing with Artin representations. If we look at this n, and pi infinity, then for n equals 2, this will be holomorphic limit of discrete series, or the other. And for n greater or equal to 3, this will be degenerate limit of discrete series, or other. Okay. So my point is that the motives that we're most naturally interested in require us to understand, to go from discrete series to degenerate things. Okay. Maybe let me also add here one last line, which is to tell you what this comes out to be in the classical case. So when G is GL2 over Q, so then discrete series is modular forms of weight k at least 2. This is weight k equals 1. There are none of these. And there is one thing here which can be described as the representation pi infinity with trivial Langlands parameter. So what I mean is that the homomorphism from WR to the L group of GL2 is trivial. Okay. So now maybe I can continue with what is known about star. So first, when G is GL2 over Q, so this is for weight at least 2. Well, for weight 2, the Galois representations were constructed by Eichler and Shimura. For weight k greater or equal to 2, they were constructed by Deligne. And this used the Italic cohomology of modular curves, so that's what this gives in the case of classical modular forms. Then here, this was done by Deligne-Serre. And this is not known how to do. Then the next case maybe is when we have GL2 over F plus, and F plus is totally real. So then, when the weights are all at least 2, so this was done by a number of people ending with Taylor, and then when the weights are all 1, I believe this was done by Rogowski-Tunnel, and then when some of the weights are 1 and others are not, by Jarvis. next, when G is SP4, so this was done by many people, including Chai Faltings, Deligne, and other people. And then, so this is the case of discrete series. And then holomorphic limits of discrete series were done by Taylor. And for SP4, there are already non-degenerate, non-holomorphic limits of discrete series. But we don't know how to attach Galois representations to them. And there are degenerate limits of discrete series we don't know how to attach. And there are these guys too, and we don't know how to do them either. And finally, when G is a unitary group, which later on I will say more precisely what I mean, then the case of discrete series has been done by Sagwoo Shin, building on work of Harris, Taylor, Clozel, Kotwitz, and other people. This is what I want to, this is the main result I want to talk about, is filling in this box. And again, once we are on a unitary group of that's not like essentially GL2, then there are non-degenerate, non-holomorphic limits, degenerate limits, and other stuff, and we don't know how to handle those. So, okay, so basically, what I would like to do is to focus on this box, on this column here, and so I will be generalizing the argument of Deligne-Serre combined with the improvements made by Taylor, as I'll say in a little while. Okay, now I think maybe I should say something. I've convinced you, hopefully, that these distinctions among the different kinds of pi infinity are important. So I should say something maybe about what they mean. So even though we want to work with a group G whose real points are possibly not connected and not semi-simple, for the purpose of the talk, let me now fix that G is a real group that's connected and simple. And let me fix H in K in G a compact Cartan in a maximal compact. And X star of H will denote the characters of H. I write delta for the roots and delta C for the compact roots, so the roots of H and K, and delta N for the non-compact roots. So let's see, I have this, and then one more thing, I want to put rho to be the half sum. Well, I will fix some fix delta plus in delta a system of positive roots. And then rho will be the half sum of the positive roots. So given this long list of notation, I can now define that a Harish-Chandra parameter lambda is an element of x star of h plus rho. So this is independent of our choice delta plus. And then lambda is regular if it's not orthogonal to any roots. And lambda is singular otherwise. So in terms of this terminology, so if lambda is regular, then there exists a discrete series pi lambda such that the infinitesimal character of pi lambda is lambda mod is identified by the Harish-Chandra isomorphism with lambda modulo the Weil group, the full Weil group. And pi lambda 1 is isomorphic to pi lambda 2 if and only if lambda 1 is congruent to lambda 2 modulo the compact Weil group, the Weil group of HC and KC. So this is the Harish-Chandra parametrization of discrete series. Now, for limits of discrete series, so now we want to let lambda be singular. So for this, we have to choose. So if we need lambda singular Harish-Chandra parameter and C a Weil chamber of G. So then the pair lambda C determines a non-zero limit of discrete series pi of lambda C if and only if lambda is not orthogonal to any C-simple compact root. So this is what I mean by limits of discrete series for G. And then pi lambda C is non-degenerate if stronger than this, lambda is not orthogonal to any compact root. Whereas here it can be orthogonal to compact roots that are not C-simple. And holomorphic, well, in this context, I can define it in terms of roots as pi lambda C is holomorphic, or maybe I should say holomorphic or anti-holomorphic if and only if Oh, so I should say here that lambda should be in this Weil chamber, on the boundary of this Weil chamber. So this is holomorphic or anti-holomorphic if this chamber satisfies that all but one of the C simple roots are compact and the unique non-compact has multiplicity 1 in the decomposition of the highest root. So this is a way in terms of roots of saying what's meant by holomorphic. Of course, holomorphic will also translate into pi being realized in H0. I mean, yeah, either that pi has QK cohomology in degree 0. And this thing between holomorphic and anti-holomorphic is between degree 0 and top degree in the various kinds of cohomology. Okay. Oh, and let me do 2 examples of this. So we take G to be SU21. And I draw the Weil chambers like this. Yes, so let me take this to be the dominant chamber. Then here, coming from the dominant chamber to this boundary, these are holomorphic limits of discrete series. Here, approaching the same points, but from this non-holomorphic chamber, are non-holomorphic, non-degenerate limits of discrete series. The same goes here. Approaching from this direction, there are, well, again, holomorphic, or you might say anti-holomorphic limits of discrete series. And finally, this point 0 can only be approached from this chamber, and this is the unique degenerate limit of discrete series for U21. So, yes?
Which walls correspond to compact roots?
Yeah, okay, so this compact wall. Yeah, sorry, so that's why I'm not approaching this wall, because if you approach this wall, you get 0. And I'm only considering half of the picture because this is also true for limits of discrete series. So the things you get here are isomorphic to the things you get here. Okay, so maybe in the interest of time, let me just stick to this one example and move on. Okay. So now let me try to give a precise statement of the main result. So okay, so for this, I want, so now G will be a unitary group associated to the data So F over F plus will be a Cm over totally real number fields. Then B will be a simple algebra with center F. V is a left B module. So associated to this data, people like Cotwitz define a unitary group, and this group will have that, for example, that if I put n squared is the dimension of the bilinear endomorphisms of V, then G, the real points, will have the form G of U P1 Q1 a product like this, where the significance of this n is that Pi plus Qi is equal to n. And D is the degree of F plus over Q. OK, so I have this group. And I also need that I have X. So this will be a conjugacy class of maps H from C star viewed as a real group to the real points G, such that Gx is a Shimura datum. So which I won't recall, but all I want, the reason I'm just introducing this X is I want to introduce E, which will be the reflex field of this Shimura datum that I will need in the statement of the main theorem. So now theorem is, so suppose pi is cuspidal automorphic representation of G such that pi infinity is the holomorphic limit of discrete series. And then I need to make some additional technical hypotheses. So I need to assume that G is quasi-split at all finite places. That the totally real subfield F plus of F is different from Q. And then I suppose that L is a prime such that pi L, the local component of pi at L, is unramified, and more importantly, that L splits in this reflex field E. Then with these hypotheses, then there exists a unique Galois representation R, L, of pi from the Galois group of F to GLN of QL bar such that, so I don't want to write things out completely because it's slightly complicated, but I just want to say that this is compatible with local Lagrange at primes P such that okay, so this Galois representation RL of pi is compatible with primes P such that, first of all, pi P is unramified. P is different from L, and for all P, for all primes of F plus above P, curly P splits in F. So this is the statement of the main theorem. And then I can make a number of comments about, well, removing hypotheses and strengthening the conclusion, but let me leave that to the end, and for now let me move on to saying something about how to prove this. So okay, so let's see, is it still here? So yeah, so okay, so let me start by saying something about what was done in this case by Deligne-Serre, since we build on their method, and then Taylor. So, so the idea was that if you start with the weight 1 modular form F, so okay, so we have F in something like this, where omega is the Hodge bundle. Then the key observation of Deligne-Serre was, if we let EP minus 1 be the weight P minus 1 Eisenstein series, then EP minus 1 is congruent to 1 mod P when normalized to have constant term 1 in the sense of Q expansions. So F EP minus 1 is congruent to F mod P. So yeah, so we can hope, well, this and the weight of F EP minus 1 is P. So while the weight of F is a limit of discrete series and only appears in coherent cohomology, the weight of F EP minus 1 is at least 2, and therefore appears in the Tal cohomology. So if this were an eigenform, then Deligne's argument for weight at least 2 would produce a Galois representation associated to this, and then we would have the Galois representation that we want, at least mod p. Now, a key problem is f ep minus 1, even if f is an eigenform, f ep minus 1 may not be an eigenform. And so then Deligne-Serre had some way of getting around this that had to do with the fact that the representations they were constructing had finite image. But in general, Taylor introduced pseudo-representations, which, if you extend this to say that f ep minus 1 to some power p to the k, p to the j, is congruent to f mod p to the j plus 1, then Taylor's method of pseudo-representations allows you to produce, well, RL of f. If I have time at the end, I can say more about this, but for now, let me move on, since this idea is completely due to Taylor, or maybe I should add sort of to Wiles in the two-dimensional case. So this is the basic idea of the argument. Then our contribution is to do this without Q expansions. So, for example, if you have if we might have a unitary group G such that the Shimura variety is compact, then there won't be any Q expansions, or even when there are, they're considerably more complicated for unitary groups than they are for GL2. So, so our method avoids Q expansions. And the way we do this is we use the Hasse invariant. So the idea is that the Hasse invariant, so it was observed by Deligne and Serre and Katz and other people in the case of GL2 that if you take this EL minus 1 and reduce it mod L, then you get the Hasse invariant of the universal elliptic curve. So we generalize this. So we no longer have this EL minus 1. We will just construct the Hasse invariant and then show that it admits a lift to characteristic 0. Okay, so to define the Hasse invariant, suppose we have A in abelian scheme over scheme S over FL. So the Hasse invariant HL, this is going to be an element in H0 of the base with coefficients in omega tensor L minus 1, where by omega I mean, so suppose this structure map is pi A, then I have the sheaf of relative differentials omega A over S. I take its direct image under pi, call this omega, and then little omega is simply the determinant of big omega. So this is what where the Hasse invariant will live. And the way it's constructed is, so we have the Frobenius isogeny from A to A upper L. And then we have, by factoring the multiplication by L map, we have a Verschiebung isogeny going the other way. And if we look at the map induced by this on differentials and pull back by the identity section and take determinants, we get a map from omega to omega upper L, by which I mean Frobenius pullback of omega. So we get something which we could call the Hasse invariant map of A. And then, well, because omega is a line bundle, this is just the Lth tensor power, and so we see that we get, and omega dual is omega inverse, so we get a section like that. And then, so here are some of the key properties of this Hasse invariant. So most important is that this Hasse invariant is compatible with isogenies. So if I have an isogeny phi of S abelian schemes, then there's a way to make sense of the pullback of the Hasse invariant of B. And we show that this is the Hasse invariant of A. So this property is important because, well, for example, if you define your Shimura variety as a moduli space of abelian varieties up to isogeny, then this is the property that tells you that the Hasse invariant is really a well-defined mod L, well-defined mod L automorphic form, where we take A the universal, well, representative of the universal universal isogeny class. Yeah. Prime to L isogeny class of over the Shimura variety of some level away from L. Okay, so this is one property. So other properties of the Hasse invariant that we need are, we need to know that it lifts the characteristic 0. So so this follows because chi faultings in the symplectic case, and then so chi faultings then generalized by Kai-Wen show that omega extends to an ample line bundle on the minimal compactification and then a general argument in cohomology shows that there exists a lift to characteristic 0. The third thing is that HL is not identically 0. So this is equivalent to the Shimura variety admits ordinary points in characteristic L. And so this is by, so there is a theorem of Wedhorn that says that if you have a given a PL Shimura variety like this, then there exists ordinary points in characteristic L if and only if L splits in the reflex field. So this is why this hypothesis that L splits in the reflex field is imposed. Okay, so these are the three main properties of the Hasse invariant. And finally, let me say, so what congruence we prove in place of this F in place of this. So first of all, what do I mean by congruence if I'm not using Q expansions? So I just mean that two things are congruent if their difference is divisible by the power of L that I want as elements of an integral space of automorphic forms. So with that notion of congruence, the result is if I take an F whose weight is holomorphic limit of discrete series, then if I look at the L to the jth power of, so let HL to the A. So maybe I should have said, so this ampleness result shows that some power of the Hasse invariant lifts to characteristic 0. Then if I take the product of this with F and act on this by a Hecke operator T, so T will be in the Hecke algebra sub capital P, where is it? I have capital P is the set of primes such that these three conditions are satisfied, then so I mean the Hecke algebra of Hecke operators with trivial component away from P, then this is congruent to just the Hasse invariant times F acting T acting just on F modulo L to the j plus 1. So it turns out that this is all that you need to apply Taylor's method of pseudo-representations instead of this to get the main theorem. Thank you.